Okay, last time we left at the point of defining distance function, and then we were talking about Minkowski matrix, where for 3 different values of R, you get 3 different distance functions. All right. So let's continue the discussion on distance functions, and let's introduce another distance function, which is very popular and commonly used in data mining and machine learning applications. It is known as Mahalanobis distance. Mahalanobis is the name of a statistician from India who defined this distance function and used in many of the studies. And since then, it has become popular and used by many people in the area of data mining and machine learning. All right. Now let's look at the equation for the Mahalanobis distance function. So if you are given 2 vectors, P and Q, or 2 points in a high dimensional space, first point is P, second point is Q, then the Mahalanobis distance between those 2 points is given by the equation P minus Q multiplied by sigma inverse multiplied by P minus Q transpose. Remember, P and Q are vectors, all right? So assume that they are vectors of n dimensions, column vectors of n dimensions, all right? Then P minus Q will be a vector. P minus Q transpose also will be a vector. And the inverse of covariance matrix, which is defined below in the second equation in yellow, is also going to be an n by n matrix. It's not going to be a vector, but it's going to be an n by n matrix. All right. And the result of this calculation is going to be a number, because it's going to give you a distance value. It's going to be a number. All right. So this distance function, as you can see here, if you were using the ordinary Euclidean distance function, then the expression for the distance function will not involve sigma inverse. It will be simply P minus Q multiplied with P minus Q transpose. But now we have sigma inverse in between. And what does the sigma inverse do? It basically assigns different weights to different variables or to different distances along different feature axes. And some weights are given, some are given more weight, some axes are given less weight. And how are these weights determined? These weights are determined based on the distribution of the data from which the covariance matrix is calculated. So if you look at this example in 2 dimensions, where we have showing you a distribution of points in 2 dimensions. So if you look at 2 red points, the Euclidean distance will be nothing but if you were to join these 2 points with a line, whatever will be the length of that line, that will be your Euclidean distance. All right. In the case of Mahalanobis distance, that you will take difference along the x-axis, you will take the difference along the vertical axis for these 2 points, and those differences will be squared up, and then they will be assigned a slightly different weight. They'll not be given the same weight, and they will be multiplied by the corresponding weight values. And then you add them up and then take the square root, and that will be your Mahalanobis distance. So in this case, if you were to do the calculations, given all those points, then you will find that the Mahalanobis distance in this particular example comes out to be 6. All right. Let's look at another example here. Okay. Okay, here is an illustration for Mahalanobis distance in 2 dimensions. And just to keep things simple, the covariance matrix in this particular case is taken to be a diagonal matrix. That means the two features or the two variables that you have do not have any correlation. And that's why the non-diagonal terms are 0. All right. And let us assume that the first variable has a variance of sigma 1 square. The second variable has a variance of sigma 2 square. All right. So that's how the matrix S is our covariance matrix. So what we can do is, in order to calculate the Mahalanobis distance, we will need to get an inverse of this matrix. So if we take the 2 by 2 matrix inverse, you can see that the inverse will also be a diagonal matrix. And the first element will be 1 by sigma 1 square. And other diagonal element will be 1 by sigma 2 square. And the non-diagonal elements will be 0. All right. So now we can write down the expression for the Mahalanobis distance, taking into account the inverse matrix. So if you look at the expression and do a little bit of simplification, you find that the Mahalanobis distance in this particular case is given as x1 minus y1 squared divided by sigma 1 squared, where x1 and y, x and y are the two variables we are talking about. All right. Plus x2 minus y2 squared divided by sigma 2 squared. So if you were calculating the Euclidean distance in your formula, sigma 1 square and sigma 2 square will not be present. All right. That is what will be the Euclidean distance. But in this case, we are basically including them. That means the equation is telling us that the features that show less variability. For example, if you look at sigma 1 and sigma 2, suppose X feature has a less variability. That means its standard deviation or variance is smaller than the second feature. Then inverse of variance is going to be larger for the first feature. That means the first feature will get more weight compared to the second. So what the Mahalanobis distance does is that it figures out how to weigh different features based on their variations. And that's the importance of this particular formula or this particular distance function. All right. So let's look at another example here. In this case, we have 2 points P and Q. Those values are given 3.9, 4.3 for the point P, 6.2, 5.2 for the point Q. And we are given a covariance matrix. In this case, the covariance matrix is not a diagonal matrix. So if you look at the elements of the covariance matrix, they are 3.05, 0.27, 0.27, and 1.93. Remember, the non-diagonal elements in the covariance matrix are going to show symmetry. All right. So that's why you have 0.27 at both the places. All right. So if you look at the Euclidean distance between these 2 points, it's pretty straightforward. You take the difference, square it up, and take the square root, and that comes out to be 2.47. Now, if you were to use the L1 norm or city block distance, in that case, all you do is look at the differences, take the absolute values, add them up, and that is the distance. So that in this particular case turns out to be 3.2. If you look at the L infinity norm, then again, you take the absolute differences along different axes, but just pick the maximum as a representative for the distance. So in that case, it is 2.3. And if you were to do the Mahalanobis distance, it turns out to be 1.41. All right. So for a given pair of points, you can end up with different distance values. All right. Now, somebody might ask, well, why do we have so many different values? Why can't we just use Euclidean distance or something else? All right. For Mahalanobis distance, I already explained to you, the main reason is that you want to give different amounts of weights or different levels of importance to different features based on how they are distributed or what kind of variability those features are showing. All right. Now, the reason for using city block distance might be, especially this is true many years ago when the computational resources were not that great. Because if you look at the city block distance, it does not involve a square operation. It does not involve a square root operation. So if you are going to be doing those calculations for very large number of vectors, with each vector with large number of dimensions, your computation time can be large, especially if you are short of resources or you do not have very high speed stuff. So that was the case many years ago. So people used to prefer that because that will make it much easier or faster to do the calculations and things like that. The same argument can be made for the chessboard distance. All right. So in general, I will suggest you use either Euclidean distance or Mahalanobis distance, depending upon how you want to proceed. All right. Any question, anything? All right. Now, what are given a function? Let us say we have a function f of two variables x and y. Can we say that this function is a distance function? That means for a function to be designated as a distance function, or if you were to write a small routine to calculate distance between two objects, for that routine to be a valid routine for calculating the distance, we have certain properties that need to be satisfied. For example, if you have 2 points, then the distance between those 2 points, whatever function you use, should be always positive. In cases when P and Q are identical, it will be 0. A distance function can never give you a negative result because you are measuring the distance. All right. At the same time, if you have 3 points, P, Q, if you have 2 points P and Q, so whether you measure distance from P to Q or Q to P, you should end up with the same result. All right. And then if you have 3 points, P, Q, and R, then if you were to take distance between P and R, that distance should always be less than or equal to distance between P and Q plus distance between Q and R. This third property is known as the triangular or triangle inequality. You can think of 3 edges of a triangle, all right? And you can see that you can take any pair of points and the distance between along that line of the triangle or that edge of the triangle is going to be always less than the sum of the other 2 edges, all right? So a distance matrix or a function that satisfies all these 3 properties is known as a distance function, or in general, it is known as a metric. So a metric is a function that satisfies these 3 properties. Let's look at the properties of similarity. So when you come to similarity, basically you can say, let's have a function S which measures similarity. Then S of P and Q is going to be 1 for maximum similarity if and only if P is same as Q. And of course, similarity between P and Q and P should be the same number, same result. So that is basically the symmetry property. All right. The triangle inequality does not get involved in the case of similarity calculation. It does not apply. So that's why a similarity function is not a metric function. It's not a distance function. It's a function that measures similarity, but does not satisfy the triangular inequality. All right. So let's see. We need to get to the next page. Okay. Okay, let's take a situation where we are given two vectors, and these two vectors happen to be binary vectors. How do we measure similarity between such vectors? All right. Now, there are a number of different similarity functions that people use. So I'm going to show you some of them. So one is known as a simple matching coefficient, SMC, which is defined as shown in the slides. And then there is another one which is quite popular called Jacquard Coefficient. Jacquard Coefficient is given by the number of attributes where P is 1 and Q is 1 divided by the number of attributes where P is 0, Q is 1, and plus where Q is 0 and P is 1, plus both P and Q are 1, as shown in the formula. All right. So Jacquard coefficient is quite popular in information retrieval, in matching text documents. It's quite commonly used. All right. So that's one of the functions that is used quite often for matching binary vectors. Let's look at cosine similarity. Cosine similarity basically measures the angle between two vectors, or the cosine of angle between the two vectors. So if the two vectors are pointing in the same direction, that means the angle between them will be 0. So they are lying along the same direction, in a high dimensional space. All right. So the angle between them will be 0, and cosine of 0 is a large value equal to 1. All right. So what one can do is one can basically use this cosine function as a measure of similarity. So this is known as cosine similarity. And the formula for cosine similarity is shown in the slide. So you take the dot product between D1 and D2, if D1 and D2 are the two vectors, and make that dot product normalize by dividing it with the length of the respective vector. All right. A simple calculation here shows you how these dot product and normalization will be carried out. And if you take these two vectors, you end up with a result of 0.3150. Remember, cosine similarity you can use for binary vectors as well as for non-binary vectors. Okay. There is another variable, another coefficient for similarity that is used, which is known as extended Jacquard coefficient, or also known as Tanimoto coefficient. And it's slightly different from Jacquard coefficient. And basically, it can be used for continuous or count attributes also. And if you apply it to the binary case, then it is equivalent to Jacquard coefficient. Now let's look at what we mean by correlation. We already talked about correlation between the features, all right? So we just want to look at the definition of correlation once again and see how it appears in the covariance matrix, all right? So if you are given two sets of readings or two vectors, vector X and vector Y, then the correlation between those two vectors is given by the formula as shown in the slide. All right. Now, if you were to calculate the covariance matrix for this data, then the covariance matrix, the first element is going to be sigma 1 square. The second diagonal element is going to be sigma 2 square if you're working in 2 dimensions. And the non-diagonal elements are going to be rho times sigma 1 times sigma 2. So the non-diagonal elements actually carry the correlation information. So that's why when earlier we looked at the Mahalanobis distance example, we had a correlation matrix where non-diagonal elements were 0. We said the features have no correlation. So if there is no correlation, the non-diagonal elements will be 0. If there is a correlation, and if somebody gives you a covariance matrix by looking at this formula that the non-diagonal terms involve rho times sigma 1 times sigma 2, you can figure out what is the value of the correlation between those features. All right. So it will be it's a correlation coefficient. So typically it will be somewhere between -1 to +1. That is, you can have no correlation, which is 0. You can have positive correlation. In that case, the correlation coefficient will have a positive value. You can have a negative correlation, then the values will be negative. All right, so let's look at an example here. So if you were given 2 sets of numbers, one can actually calculate the correlation. This example shows you how to do that calculation and get, yes, please. The previous slide?
Or this slide. Square root function. Inside this function, there is for to square the whole value, the summation value for each subtraction.
Basically, you will be doing the subtraction, square, and then taking summation. Okay. All right, so let's move on. Here is a nice plot which basically gives you a pretty good idea of visually figuring out the correlation. So suppose you have a collection of observations where each observation has 2 numbers. That means you're talking of a 2-dimensional vectors. So you are given a collection of vectors. Each vector has 2 elements. And what you do is you plot them on a graph paper. All right. So once you plot, that plot is known as a scatter plot. So what we are showing here is a set of scatter plots. All right. So if you look at the topmost scatter plot on the left-hand side, basically it's a diagonal line, more or less, going upwards. All right. So the orientation of this line tells us, and since it's a line, tells us that the 2 features are highly correlated. The correlation coefficient is 1, but it's a negative correlation, because if one is increasing, the other is decreasing. That's why it's a negative correlation. If you look at the plot at the end, at the bottom line, which is a reverse case of this, here again correlation is 1, but now it is positive correlation. So coefficient is +1, while in the top case it is -1. So if one feature increases, the other feature is going up, that means they are positively correlated. If one feature increases, the other feature goes down, that means they are negatively correlated. And if one feature increases and the other feature does not care, that means they are totally uncorrelated. And if there is a small amount of correlation, then that correlation, depending on positive or negative, you will get a cloud of points oriented in one way or the other way. So if you go through all these pictures, you'll find that right in the middle, we have a correlation of 0, where the points are X and Y variables are moving independently of each other. So it turns out that in that case, the plot is going to be more or less very circular in nature. All right. For rest of the cases, the circles will turn out to be ellipses, or kind of you can press that circle one way or the other. And depending on positive or negative correlation, these ellipses will have different orientations. All right. So that is what we mean by correlation. Now, when you are dealing with objects where each object is described by a number of different properties or different attributes, some of them continuous attributes, some of them nominal attributes, some of them ordinal attributes. So question is, how do you measure the similarity between such a pair of objects? So the answer is very simple. That is, you first measure the similarity between the ordinal attributes of the two sets of points or two sets of vectors. Then you measure similar thing between the nominal attributes, measure similar thing between the continuous attributes, and then you can combine all those similarity values through some proper weight values. And that's how you can end up with a single number which represents the similarity between those vectors or between those objects. All right. So that's how typically it will be done. And obviously, you can assign different weights to the different components of the similarities. And again, that will depend on a particular problem. It also depends on what kind of variables are involved and how, as a user or as a designer, you weigh different variables, give them different importance, and so on and so forth. All right. Now, we mentioned earlier that in order to characterize a data set, you are talking of the number of dimensions, whether it is sparse or not, and what is the granularity of the data set at which the readings have been taken or the measurements have been done. All right. So once you have a collection and you are embarking, let us say, on a data mining project, the first thing you want to do is you want to get a good idea about the descriptive statistics of your data set. That is, you want to understand what kind of attributes we have, what their ranges are, what are the means, what are the variances, and things like that. And some of the terms here, mean, median, mode, percentile, variances, standard deviations, etc., are very familiar to all of you. All right. So basically what we have done is, in the next few slides, some of these things are shown or done. And we will take an example to show some of these things using a very well-known data set, which is known as the IRIS data set. This data set has 3 classes of objects, and objects are flowers in this particular case. All right. So there are 3 classes of flowers, or 3 types of flowers. And the original data set has 4 features or 4 attributes, which I mentioned earlier also in one of the lectures: sepal width and length, and petal width and length. All right. So let's look at this data set, and this very common data set, because it's a very small data set, easy to understand, easy to explain, and easy to illustrate different concepts. So definitions for mean and median, everybody knows. So let's just move on. All right. Similarly, how the features are varying, we can measure that in terms of variance. And also there are a couple of other things that people can use, like absolute average deviation or median absolute deviation, etc. All right. But most commonly people end up using variance. other than getting these mean variances, mode, median values, etc., it's very common to visualize the data and take a look at data through your own eyes to understand what's going on in the data and what kind of relationships or properties might be present in the data. All right. One way to look at the data is to do histogramming. That is, if you have certain attributes which are continuous attributes, obviously that attribute varies over a range. So what you can do is you can divide that range into number of bins and then find out how many values fall in each bin. So that will be basically histogramming. So you can generate a histogram or histograms for different variables and try to understand how the values are distributed. Instead of doing one-dimensional histogram, that is looking at one attribute at a time, you could look at two-dimensional histogram, that is look at a pair of attributes and see how that particular pair of attributes is distributed through histogramming. So in this case, we are showing you the distribution of petal width and petal length in 2 dimensions for the iris data set. All right. So this gives us a slightly better picture of how these two particular features are varying and how they are occupying different bin values. Sometimes people like to make use of what we call as box plots. A box plot, as shown here, basically has a shape of a box with a few lines on it. So there will be a line at the bottom, which is basically the lowest value. So if you look at petal length box plot, the line at the bottom, lowest line, horizontal, small horizontal line, these lines are called whiskers. So this line is representing what is the lowest value that you have per petal length. Similarly, the top whisker at the very top, small horizontal line, tells you what is the maximum value that you are seeing. All right. Rest, the box encloses the rest of the values, and the red line in the box indicates where is the median for the plot. All right. So typically, graphically, you try to illustrate where is the median, what are the lowest value, what is the highest value, and so on and so forth, just to give you an idea of what's going on or how the data is distributed. The scatter plots are really most useful plots, so I prefer to use them to get an idea of what's going on. So what happens in a scatter plot is that you will take 2 or 3 variables at a time and try to plot them in the form of a scatter plot. All right. So if you do 2 variables, then you get a 2-dimensional scatter plot, which is easy to understand, easy to look at. Sometimes people can do it in 3 dimensions, but that's hard to do the interpretation and all that. All right. So let's just look at scatter plots in 2 dimensions. All right. And let's see. So in this plot here, in this slide here, we are looking at the scatter plot of iris data. All right. So remember, there are 4 features in the iris data. All right. So if you look at the plot right at the bottom of the left-hand side, it's a plot between sepal length and petal width. All right. So if you look at on the vertical axis, we are, the bottom row is for petal width, next row is for petal length, next one is for sepal width, and top row is for sepal length. And similarly, we have 4 columns corresponding to 4 attributes. All right. So except the diagonal columns, where we are talking of the same attribute, rest of the cells or rest of the blocks represent a pair of attributes. So what we are doing here is we are showing how those values are distributed in that particular block. Now, in this case, the data comes from 3 distinct classes. So it's very common in a scatter plot to color code the underlying points by the class label or representing the type of the class that data comes from. All right, so in this case, since we have 3 classes, so you will find that we are using 3 colors to plot the point. All right. Now, one thing you can notice from this plot, for example, let's go to the second row from the top and the last column and second row in the last column. All right. You can see that all the violet points are nicely away from a red and green point. All right. That means by looking at this, we can see that if we were to look at petal width as a criteria to make a distinction between flowers known as setosa from the other 2 classes of flowers, we can do that very easily by setting up some threshold point along the petal width axis somewhere midway in that gap that we have there. All right. So looking at scatter plots, one can get a decent idea about how difficult is the underlying problem if you were to build a classification model. Or you can get an idea how difficult is given problem if the data shows a lot of intermingling, a lot of overlapping. Obviously, you are dealing with a tough problem. But if the data shows that points with different colors are nicely separated, obviously, then you are dealing with a very simple problem. So by looking at a scatter plot, one can get a fairly good idea about how difficult is going to be the problem at hand for which you're trying to build a model. All right? Any question? Okay. There is also possible to do visualization through parallel coordinates. I'm not a great fan of this, but I just wanted to mention it, what you can do. And I think in the next slide, we have a plot for the iris data. So if you were to use parallel coordinates, that's how the plots will look like. And again, you can see that the violet color points are kind of easy to separate out. So you can get a similar result that we got from scatter plots, that it will be easy to separate these particular class of flowers from the other 2 classes. All right. There are a few other types of plots known as star plots and Churn-Off faces. Some people use them. And again, here is an example of star plot for the iris data. And I think here is an example of Churn-Off faces for iris data. Okay. So again, you are representing each vector through a face. And it turns out that all the vectors that come from class Virginica show similar faces, and all the points that come from class Setosa, they have different kind of faces and things like that. Okay. Again, just a way of representing information. So let us summarize what we have done so far. Make sure to visualize data via histograms and scatter plots to get a feel for the complexity of the problem. So anytime you start working on a data mining problem, that is what you should be doing. All right. And also you should consider visualization or dimensionality reduction via mapping from high dimensional to a low dimensional space. And that is what we will be discussing next. But before we do that, I think we will take an example of data visualization to go over all these steps using the Python libraries that we have discussed earlier. So it gives you an idea of what is expected. So the example that we are going to be taking is based on housing data, which is known as Boston housing data. This data was collected in 1978. So it's a pretty old data set. It has 506 entries, or you can say 506 vectors. And each vector or each entry consists of 13 features or attributes. Those are independent features and one dependent feature. That means the dependent feature has a value which is a function of those 13 independent features. All right. And this data is available at UCI Machine Learning Repository, which is one of the main repositories for this kind of work. And it is also included in sklearn library for machine learning. What are the features? So here is a list of the features. All right. For example, CRM, the first feature, which is basically per capita crime rate by town. So this is basically a data taken over Boston area. And what they have done is they have towns in that area. So for each town, they have aggregated the data, and each town is being represented, or a particular geographical unit that they have defined is being represented by these 13 features. All right. So these features are not representing individual houses, but they are representing geographical entities, which you can call as towns or tracts or whatever it is. All right. So basically, there's a per capita crime rate, proportion of residential land zoned for lots over 25,000 square feet, and so on and so forth. All right. One thing I want to mention about this data set, because as I said, this data set is included in the sklearn library, but I think if you go to the latest version of sklearn library, you will find that this data set is not there. This has been withdrawn. And I want to mention that reason here, because that is, again, an important point in terms of data mining, machine learning, and AI. So look at the third feature from the bottom. This is an attribute B times 1,000 or whatever it is, something. That's how it's measured. It is defining the proportion of African Americans in a town. All right. This is not an acceptable feature nowadays. All right. This was something that they could do it in 1978. But as per current practice, anything that is violating the ethics and is kind of discriminatory in nature and trying to exploit certain features or factors that tend towards race-based or skin-based decision-making, that is a big no-no. All right. So this data set, I think, has been withdrawn, but I had these results and I wanted to make this point. So that's why I said I will use this example, but at the same time, I will make that point so that all of you remember this particular concern that we have. And this concern is not only present for this particular example, because there are reports where, people have built loan approval models and some other those models are biased in terms of certain segments of population. There are a couple of other models that people have built for hiring, etc. And again, it turns out that many of those models are biased against women and so on and so forth. So in recent years, in machine learning, in data mining, in AI, this issue has been realized that when we make use of the data and we do not pay attention to some of the things, then we will end up with models that are unethical, that are biased, and that should not be used. All right. So with that, let's look at this data and see how one can do visualization, because whatever visualization we do, that applies to any kind of data set. All right. So first thing we want to do is to import all the necessary libraries. Okay. So basically we will be importing NumPy as NP, Pandas as PD, and we will be making use of matplot library. So we import that and we can define whatever style of visualization we want to use. All right. So once the necessary libraries are loaded, next step will be to get the data. So in this case, when this example was created, we were able to import the data. So we import the data and then we take all the independent features and put them into vector X, into matrix X. And then we take all the dependent, there's only one dependent feature. So we take that dependent feature and put that into column vector Y. All right. So at this point, if you look at X, X is going to be a matrix of size 506 by 30. Why 506? Because we have 506 examples. And 13 is the number of features that are independent for every example. So that is the size of matrix X, all right? And you can print out the names of the features, and that has been printed out. And as far as Y is concerned, Y is going to be a column vector with 506 rows, all right? Because it's only one value per record, that is the dependent. All right. So we got the necessary libraries, we got the data. So let's see what we can do next. All right. So first thing we can do is we can make use of Pandas functionality to look at the descriptive statistics. So get the mean, count, standard deviation, minimum, what are the 25th percentile, 50th percentile, 75th percentile, maximum value, etc. All right. So all those can be calculated through a single statement once you have the data in the form of a data frame in your Pandas. All right. So that is what we got. And one can look at these numbers and try to get some idea of what's going on. Suppose we are interested in doing box plotting. So we can make a box plot of some of the features. All right. So here is just an example of how you will do the box plot. All right. Now what we can do is we can look at each of these independent features and try to do the histogramming. By histogramming, we will get an idea of how the values are distributed and what kind of distribution pattern we might have. All right. So here are 13 plots that show you how the values are distributed. And you can see that in some of the plots for some of the values, there are certain values that are highly dominant because the corresponding bar is really, really high, and the rest of the values are really not that values are present. Okay. Or for example, this might be a modal histogram. For example, if you look at the fourth histogram of the first row, you have only 2 bars, all right? Because one of the variable turns out to be a binary variable. So for that binary variable, that is what you will get, all right? So these histograms tell us how the data is distributed, all right? Whether it is concentrated in one corner of the range values or concentrated in other corner, or it is kind of distributed over most of the values and things like that. This is the plot of dependent variable, because dependent variable in this case is based on those 13 features. They are trying to figure out what is the housing value or median value of the houses. All right. So that's a plot of median housing values. And roughly one can say that this is a kind of bimodal plot. The first part of the plot up to kind of 40 along the x-axis range kind of looks like more or less Gaussian. And then there is a small there are, the other part after 40 is not, Gaussian, but it has a distribution little different from the Gaussian distribution for most of the values. So in some sense, it's a bimodal plot, one mode being nicely Gaussian and other mode it's just, there, okay? Now, what we can do is, and this point is really important, ultimately, when you have data like this, what you're trying to do is you're trying to figure out what is the relationship of the dependent variable with different independent variables. So the best way to guess or to visualize that relationship is to do a scatter plot of the dependent variable with independent variables one at a time. All right. So in this case, what we have is 13 independent variables. So basically, we end up with 13 scatter plots, each independent variable paired with the dependent variable. All right. So we have 13 plots, and these plots can give us an idea of how each variable is impacting the dependent variable. So in some cases, there is a positive correlation. In some cases, there is a negative correlation. And in some cases, it's not, the correlation is not that clear. All right. So basically, by doing this kind of visualization, one gets a good idea in terms of how the dependent variable is related with different independent variables. And by doing a scatter plot of the pairs of independent variables, one can get an idea of how they are correlated and how they are related with each other. So typically, before you embark upon any model building project or any project that you want to do, once the data has been collected, this is the first step you should be doing. That is going through the visualization of the data to get a better feel for the data. All right. Any question, anything? Okay. All right. So that basically takes care of the data and data mining component. And what we are going to do is we are going to move on to the next topic. All right.